Today, we're diving into a really weird feature of our planet's magnetic field. It's called the Equatorial Anomaly. Now, it's a totally real phenomenon, but the why? Well, that's where things get contentious. We're going to explore a very different theory, one that pretty much throws the standard explanation out the window. All right, so what is this thing? Just imagine you're looking at the Earth's ionosphere, that layer of charged particles way up high. You'd expect it to be a pretty smooth blanket, right? But it's not. Right over the magnetic equator, the concentration of particles actually dips down, creating a kind of trough. And then, just to the north and south of that dip, it piles up into two big crusts. That's the Equatorial Anomaly. It's a real puzzle, and explaining that very specific shape is the whole game. And that really gets us to the heart of it. Mainstream science has a model for this. It involves complex electric fields and plasma drifts. But is it right? The source material for this explainer argues pretty forcefully that the official story has some serious, fundamental problems. So before we can even get to the new theory, we have to understand what's supposedly wrong with the old one. Let's take a look at the arguments against the standard model. The author of our source material does not beat around the bush. He takes a look at how the standard model is described and immediately sees what he calls a basic contradiction in physics. The idea that something diffuses under gravity but somehow moves higher just doesn't compute for him. And this is really the opening shot of his entire critique. And the critique just keeps building from there. First, he argues that the electric fields you need to make the anomaly work just don't line up with our diagrams of the main geomagnetic field. Then there's this huge problem. The model needs a powerful eastward electric current, but there's no explanation for what's powering it. It's like a circuit with no battery. He also points out that this is totally different from how we see currents behaving at the poles. The author's conclusion? It feels less like a genuine explanation and more like someone was just plugging in numbers to make the math fit the data. And this slide really nails down that central issue. The standard theory hinges on something called XB drift. The math works out. An eastward current crosses the magnetic field, and poof, you get an upward force that lifts the plasma. But the author asks a dead simple question that cuts right through the math. Where's the power source? What is driving this current? Okay, so after laying out all those problems, the author proposes something completely different. It's a new model that isn't based on external fields at all, but on a fundamental charge moving up from inside the Earth itself. So here's the big idea. Forget about plasma getting pushed around. This series says there are these foundational streams of charge, photons specifically, that are constantly moving up from the Earth's interior. You've got two huge streams, one from each pole, that curve and cross each other deep below the equator. And that crossing action, he says, is what causes the whole anomaly. So how does crossing streams create a trough? Well, the theory proposes this really unique mechanism he calls spin cancellation. The idea is that these streams of photons have opposite spins, and when they cross at just the right angle, those opposing spins literally cancel each other out, creating a zone of lower energy. And that zone of lower energy is the trough we see at the equator. Let's just walk through that real quick. Two charged streams are heading toward each other from opposite poles. As they move, the Earth's rotation squishes their paths from perfect circles into ellipses. Now that's the key part, because it makes them cross at an angle less than 90 degrees. And it's at that shallow angle that the magic happens. The opposing spins cancel out, and you get your energy trough.
Okay, so spin cancellation could maybe explain the dip at the equator. But wait a minute. The anomaly has two parts, remember? What about those two big peaks of ionization at 17 degrees north and south?
And this is where things get a little tricky, even for the author's own model. Based on the pure geometry of his theory, those charge streams should actually pop up at the surface at 30 degrees latitude. But when we actually measure where the crusts are, they're found at 17 degrees. That's a 13-degree difference. So how does the theory explain that gap?
The author offers a two-step answer. First, he says the natural curve of the streams as they rise already brings them to a lower latitude. But then, a second effect kicks in, something called an atmospheric Z-pinch. Now, this is a real thing in plasma physics. Parallel currents attract each other. The author suggests this effect literally pinches the two streams even closer together, pulling them from that predicted 30 degrees all the way down to the observed 17.
Now, you have to admit, this is a pretty unconventional model. So to back it up, the author tells us we need to look for evidence not here on Earth, but on another planet in our own solar system. He points us to diagrams of Jupiter's radiation belts made from data gathered by Voyager 2,
And he argues that if you look closely, these diagrams show a very clear split, a gap, right at Jupiter's equator. This, he claims, is a perfect visual match for his model of crossing charge streams. It's his smoking gun.
So why don't we see that same split in diagrams of Earth's Van Allen belts? Well, he argues that the diagrams we usually see are old, super simplified cartoons from the 1950s. They're just not detailed enough to show a subtle split like that, even if it was there. So why the difference? Why do we get detailed maps for Jupiter but cartoons for Earth? Well, the author has a pretty provocative theory about that. He suggests that the more detailed, complex diagrams of Earth's fields are kept under wraps because they might actually support his theory and challenge the mainstream models. He goes even deeper, arguing it's not just the diagrams, it's the methods we use to collect the data. For Jupiter, we used a technique that maps local electron energy, which he says clearly shows the split. But for Earth, he claims, the data often comes from methods like omnidirectional proton flux, which basically averages everything out. A perfect way, he argues, to hide a split right at the equator. And this is where this alternative theory takes a sharp turn, from a scientific argument into some very, very strong and controversial conclusions about the scientific establishment itself. The author brings up these real-world proposals you sometimes hear from scientists about trying to drain parts of the Van Allen belts to make things safer for satellites. From his perspective, this isn't some brilliant idea. He sees it as proof of a profound, even dangerous ignorance about how our planet's systems actually work. Why would it be so dangerous? Well, in his model, trying to drain the belts is like trying to scoop a hole in the ocean. It would just fill right back up, because the field is constantly being fed from the sun and the galaxy. But he says it's worse than that. He predicts that an artificial drain would cause a massive surge of ionization up from the ground, which he thinks would be absolutely catastrophic for all life and all technology on the surface. And this all leads him to his final and most extreme statement. He argues that this kind of thinking, proposing these huge, potentially destructive projects without fully understanding the consequences, is a sign of a deep problem. It's a very strong claim, and it's the conclusion he draws from his entire line of reasoning. And that's where we're left. We started with a little puzzle in our upper atmosphere and ended with a fundamental challenge to mainstream physics and a stark warning about scientific hubris. It really makes you step back and ask a much bigger question. In a world of established science, how are new ideas, whether they're right or wrong, born, debated, and heard?